So now let's do a problem like this with some context. So in 2018, a Gallup poll asked 1,009 random adult Americans whether public smoking should be banned in the U.S., and 58% replied yes. There are 200 million U.S. adults. Lovely. And this is a real data set because I have a source link there, so this actually happened. All right, so which type of observational study is being conducted? So obviously this is observational. So let me just remind everybody. Cross-section is when you're taking a snapshot in time. Right? Case control is when you're doing a retrospective, looking back into the past at existing records and comparing groups. And then there's a cohort study when you've been watching one group of people over an extended period of time. Right? So this is watching over extended period. This is looking at past records. And well, it can be the past or records or both, but here I'll just say past records. That's the most common way to do it. And then this one, which is obviously the one we have, is a snapshot in time. Right? You're asking them a question right now about how they feel right now about public smoking. Current moment. All right. So there we have it. Just a little reminder, a little review of section 1.2. That's where that came from, in case you want to go look it up and read more. All right, so now we're going to verify the conditions of our central limit theorem for proportions are met. Now, I just want to remind everybody that we have two sections in this chapter, and one involves the central limit for the means, right? And so the central limit theorem for the means has random, independent, normal, and so does the central limit theorem for proportions. And so you have to keep them straight, right? Central limit theorem for proportion also has random, independent, normal, and they're the same for the two first bits, but it's the third bit that's different. All right, so we're looking at the central limit theorem for proportions. This is from my exam notes packet, but it's also a few pages earlier in the notes. All right, so we want to verify those conditions. Well, the conditions are random, independent, and normal, right? So random, independent, and normal. All right, random is the easiest one because random is given. I wrote it right up here at the top. Given. So random is yes because it's given. Right? It's literally written in the problem that it is normal. All right, so independent is a little bit tricky. Independent, you need your little sample size to be less than or equal to 0.05 of your capital N. Now our little sample size here is 1,009, and it doesn't hurt to kind of label that out for yourself, right? That's your little sample size. All right, so 1,009 is less than or equal to 0.05. Now capital N. Capital N, this was a poll of adult Americans. So capital N is all adult Americans. Ah, but we know what that is because it says right here. I actually gave it on this one. So we'll actually be able to find this, 210 million, which is a really big number, right? So we can just kind of say, of course it is. If we want to go find it, which, you know, we could, there's nothing stopping us, we could go find that value, and sure enough, it would be, right? So you can kind of just say, you know, of course. The only time you actually have to do this multiplication and work it out is when it's close, right? But I can prove, by the way, that this is the case, just so you believe me. So here, let me bring Desmos up. Okay, so 0.05 times 210, that's 210 million. And it's 10,500,000. So indeed, it is quite significantly larger. So if you wanted to, you could find that number. That's fine. All right, so that's a yes for that one, and we've proven why. That's a yes, and we've said why. Normal. All right, well, normal's going to be a yes also, but we're going to prove it. And it's not always. I mean, you never know. Some project or something you're working on might not work out to be normal. But in the central limit theorem, it says to be normal, we have to have npq be greater than 10. That's the way it is for proportions. All right, so we need npq. N was 1009 times p. P was right here. And again, it really pays to kind of write these out for yourself. P is 0.58. So I'm just going to put parentheses around it and say 0.58. And then Q is the complement of 0.58. So Q is the 1 minus that, right? So it's 0.42. Now, if you don't believe me, I will, of course, go find it in Desmos. I would not lead you astray, right? So 1 take away 0.58 is indeed 0.42. And then I'm actually going to go find that value. 1009 times 0.58 times 0.42 is 245.79. So it's way bigger than 10, which is what was required. So this is 245.8, which is bigger than 10. So that's a yes also. All right then. So we've got that going on. Lovely. So now we need to be able to describe the sampling distribution. So we found the random independent normal bit. Now we're going to describe that sampling distribution. So that's when we get into the shape, the center, and the spread. That's describing the distribution. So distribution has 3 qualities. So shape, and again, I don't really need explanations. I just need formulas, symbols and formulas. All right, so shape is normal. We just proved it above. Center, well, it says right here, maybe I should have highlighted it. The center is the mean of the p-hats, right? And the spread is right here, right? Or here, same thing. Okay, so it's the mean of the p-hats, mu sub p-hat. So mean of the p-hats, which is p, but p was given. It's 0.58. And the spread is the sigma of the p-hats, or if you like, it's the standard error of the p-hats. Either way, it's the big square root p times q over n, which would be 0.58 times 0.42 divided by 1009. All right, again, I will reiterate, type this carefully. Into Desmos or your calculator, right? You have to enter those values very carefully to get this to work. All right, so I'll hit the square root button, and it's easiest if you just hit division right away. So if you hit division right away, then you have it. So 0.58 times 0.42, and then 1009, and I get 0.0155379, so 0.15538. So remember, we want a lot of decimal places for that one. So we're going to go 0.015538. Again, keep a lot of decimals. Keep 5 or 6 decimal places. Actually, I would say 6, sometimes 5, but at least that much. And also note, we're going to use these values as the mean and standard deviation in our normal calculator from StatCrunch. That's key, right? You don't want to lose sight of that. You're finding those values for a reason. The center and the spread will become the mean and the standard deviation of your normal calculator, respectively. All right, so let's do one. Let's do one problem. Okay, so it says find the p parentheses, so that's looking for the probability. So when we want to find a probability, we'll put our mean and our p hat in, or standard error of the p hat, excuse me, and we'll enter the p hat value, which is 0.60. Right? You can't type 60. You have to make it into a decimal, of course. All right, so let's do that. And I'm going to again make this smaller so we can kind of see both things side by side here. All right, so StatCrunch right here. I'm going to go to Stat, Calculators, Normal. Let me move this over. All right, so the mean is 0.58. The standard deviation is 0.015538. Again, you want to keep 5 or 6 decimal places to keep your accuracy up. And they want to do a greater than, so we'll switch to a greater than sign. And then we're going to make this 0.60. So we'll make a little note. That's p hat greater than 0.60. Okay. All right, and we have our picture. It's drawn for us and everything. We can tell this is 0.60 down here, right, where that line falls. Oh, sorry. There you go. So then we want the probability that p hat is greater than 0.60 equals, or it's approximately, 0.0990. That's what was being looked for. And they want 4 decimal places. So it's a 0 at the end. Technically, you don't have to write it when it's a 0 at the end, but I already wrote it, so I'm just going to leave it there. All right, I'm going to show how to do that last bit in a calculator, a TI calculator. So if you're not working on a TI calculator, you can just skip ahead. It occurs to me I never actually showed how to do the square root thing for the spread in the calculator, so let me show that real quick. So you take the square root first, and you do 0.58 times 0.42. And just like with Desmos, you don't want to arrow your way out. You want that 1009 division by 1009 to be in underneath that square root. And then you press enter. So there you have it. All right, so now we're going to use normalcdf because it's a probability question. So we grab number 2. We say 0.6 is our lower, because that's the lower edge of what we're shading here. And then 1e99, because we're going to infinity. We say 0.58. And we say 0.015538. And paste it and press enter. And there you have it. Same answer as that they received with StatCrunch. Oh, and let me write that down too. So if you want the TI, again, this is only for people that are working with a TI calculator. If you're not working with TI calculator, then just skip ahead. So they would write 0.6, 1e99, 0.58, and 0.015538.